Hello and welcome. This is Cambridge O-Levels Chemistry Paper 4 Alternate to Practical. The subject code is 5070. This is May-June 2022 exam. And this is the variant 2 of this paper. Let's start. Question number 1. It says, a student determines the concentration of aqueous potassium manganate, KMnO4, by titration with a solution of ethane dioic acid, H2C2O4. An equation to represent this reaction is shown. 2 times KMnO4 plus 5 times H2C2O4 plus 6 hydrogen ions gives us 2 times manganate ions plus 10 carbon dioxide molecules, 8 water molecules plus 2 times potassium. So below are diagrams of some of the pieces of apparatus the student uses are shown. A, B, and C. So name the pieces of apparatus. So remember this A, the apparatus A over here is the burette. Call it B-U-R-R-E. Sorry, B-U-R. It's burette, B-U-R-E-T-T-E, burette. The part B, the apparatus B is pipette. This pipette. And C is the conical flask. Conical flask. Okay. Then part B, it says the student records the mass of a sample of solid ethanoic acid, dissolves the solid in distilled water and makes solution up to 250 centimeter cube, uses apparatus B to transfer 50 to 25 centimeter cube of solution of ethane dioic acid to apparatus C, adds 10 centimeter cube of dilute sulfuric acid to apparatus C, fills apparatus A with potassium, the solution of potassium manganate, titrates the colorless solution of ethane dioic acid with solution of potassium manganate till the end point is reached. Repeat the titration 3 more times. Okay. Then it says, suggest why sulfuric acid is added to the apparatus C. So basically, when we add the sulfuric acid, it increases the acidic content and it prevents the magnesium KMnO4 or basically manganese oxide to reduce to manganese MnO. So basically it prevents the oxidation of MnO4 to MnO2. So if we add sulfuric acid, it gives this, and it also prevents the oxidization of manganese oxide. Basically, what exactly it's doing. So basically, so let's write it. So it basically prevents the oxidation of, you could say oxidizing, the oxidizing to and manganate oxide and oxidation of manganese oxide by increasing the acidic content or H positive ions in the solution. Okay, so this is how it's done. So then it said state the color change at the endpoint. So initially the solution change is colorless. It is colorless and it changes to pink. Okay. Then part 3, it says diagram shows parts of apparatus A at A with liquid levels at the beginning and end of titration. So initial reading, we can see it here. It is somewhat this, and then final reading is somewhere here. Then it says record the values in the table. So final reading, initial reading. So if you're going to use it, so initial reading is 1.7. Final reading is 27.1. So we used it. So final reading is 27.1. Initial reading is 1.7. Volume used, if we subtract that, it becomes 25.4. Okay, let's complete the other table. It becomes 25.1. This comes out to be 0.3. So from these values, we have to determine the best titration result. So best titration result, we can say that the difference between these two, the difference between these two is 0.2. Difference between these two is 0.3, and difference between these two is again 0.3. So good titration results can be considered as this and this. Okay. Or another way is to when we have to best titration results, we have to find a good way is to take out the average. So or complete average. So if we are going to take the complete average and see which are the nearest to those average, and those will be a good one. So again, but if we have selected these two values and from these two values, what we can say is that 24.8 plus 24.6 divided by 2 is equal to 24.7 centimeter cube. So the answer will be 27.3 centimeter cube. So moving on. So moving on, part C, it says another student repeats the experiment using the same method. This student uses 1.08 grams of ethane dioic acid to make up 250 centimeter cube of solution of H2C2O4. The student obtains an average titration volume of 24.55 centimeter cube. So it says calculate number of ethane dioic calculate number of moles of ethane dioic acid in 25 centimeter cube of H2C2O4. That is actually show you working. So MR of this is 90. So number of moles, remember, number of moles is mass in grams divided by MR. So mass in grams of H2C2O4 divided by the MR. Mass in gram is 1.08 and MR is 90. So number of moles comes out to be 0.012. These are the number of moles. So concentration. So basically we have what? So we have concentration as 0.012 moles in 250 centimeter cube of water. So the in terms of what the number of moles in 25 centimeter cube. So if we have to find out the number of moles in 25 centimeter cube, just simply say that 0.012 moles in 250, or the other way around. That would be easier for us to write. So 250 centimeter cube has this much moles. 1 centimeter cube will have 0.012 divided by 250, and 25 centimeter cube will have 0.012 divided by 250 multiplied by 25, and this is 0.0012 moles. So the answer will be 0.0012 mole of ethane dioic acid. That will be in 25 centimeter cube of the liquid. Then it says during the reaction, 2 moles of KMnO4 react with 5 moles of ethane dioic acid. Calculate number of moles of KMnO4 in 24.55 of aqueous potassium manganate. So remember, when we have 5 moles of ethane dioic acid, we require 2 moles of KMnO4. We have 1 mole, we require 2.5 moles of KMnO4. Now, how many moles we have? We have this much moles. Remember, we have this much moles. So we have 0.0012 moles, and this will give 2 by 5 multiplied by 0.0012, and this will give us 0.00048 or 4.8 into 10 to the power minus 4 moles. So answer will be 0.00048 moles of potassium manganate. That would be in the solution. So moving ahead, it says calculate concentration in moles per decimeter cube. So moles per decimeter cube of KMnO4 or aqueous. To give yes. So how many moles we have? So we had 4.8 into 10 to the power minus 4 moles in 24.55 centimeter cube of this. And remember, 1 decimeter cube is equal to 1000 centimeter cube. So just so we have almost this. So if we have, we can say we basically have to convert this. So other way, 24.55 centimeter cube has 4.8 into 10 to the power minus 4 moles. Then we have 1 centimeter cube will have 4.8 into 10 to the power minus 4 moles divided by 25.4. And if we have 1000 centimeter cube, this will have 4.8 10 to the power minus 4 divided by 24.55 multiplied by 1000. This will be the value, and this value turns out to be 0.0196 moles per decimeter cube. Okay. Then it says calculate the concentration in grams per decimeter cube of potassium manganate. Give your answer to 3 significant figures. So remember, concentration in grams per decimeter cube is equal to concentration in moles per dm cube multiplied by m. So what's the concentration in mole per dm point? 0.0196 moles per dm cube multiplied by mr. mr is given to us as 158. Multiplied by 158, you get 0.0968 grams per decimeter cube. So we have to give, remember, up to 3 significant figures. So it will be 3.097 grams per decimeter cube. So this will be our answer. So this is how we solve this question number 1. Then moving on, question number 2, it says a solution contains 1 cation and 2 different anions. The table shows tests a student does on this solution. So it says complete the table and name any gases formed. So what the student is doing, the test is 1 centimeter cube, 1 centimeter depth of a solution in a test tube, add small volume of aqueous sodium hydroxide. Then add more aqueous sodium until it is excess. The cation might be aluminum Al3, the cation could be. So if there is aluminum 3, there will be a white precipitate. So white precipitate forms. Okay. If we add more sodium hydroxide until it is in excess, the cation, there is white precipitate also for zinc as well, and Zn2 positive, and this precipitate dissolves in excess. The precipitate becomes colorless. So there is a chance of two cations. So what we can write? So precipitate dissolves colorless solution. Okay, so precipitate dissolves in excess. You can write in excess in colorless solution, or the solution turns colorless and no precipitate remains. So moving ahead, part 2, it says 1 centimeter cube depth of solution in a boiling tube, add a small volume of aqueous ammonia. Then add more aqueous ammonia until it is in excess. And then it says the cation is Al3. So remember, in this case, white precipitate will form, and the excess ammonia, the precipitate will remain. So for first, and that is a test for Al3 ion. So number 1, which says white precipitate forms. Then we have precipitate is insoluble in excess. That's what we have to write. Precipitate insoluble in excess ammonia. Okay. Then part 3, it says to a depth of 1 centimeter cube solution in a test tube, add nitric acid and warm until no further change is seen. A gas is evolved that decolorize acidified potassium manganate solution. So remember, it decolorizes potassium manganate. It means that there is an acidic gas, or it's actually sulfuric or sulfur dioxide. So the gas is sulfur dioxide or SO2. One of the anions is sulfate, basically SO4 2 negative. Okay. Then it says to the solution 3, add aqueous silver nitrate. A yellow precipitate forms. The other anion is, so remember, a yellow precipitate, or basically it would be a silver precipitate, and silver precipitate with a yellow color is silver iodide, basically AgI. So other anion is iodide. So you can write it as iodide ion or I negative. So moving ahead, it says part B. It says a mixture of solids contains barium sulfate and sodium chloride on. So remember, barium sulfate is insoluble in water. Oh, again, it has written it right. So barium sulfate is insoluble in water and sodium chloride is soluble in water. So one is a soluble salt and one is an insoluble salt. So first of all, it says describe how you separate a mixture to obtain pure barium sulfate and pure crystals of sodium chloride. So the easy thing is, say we take a beaker and fill it with water. So you fill it with water and add both salt. Add NaCl and also add barium sulfate. Okay, so the NaCl will, this will dissolve, whereas barium sulfate will remain inside water. So the solution will look something like this. So you have a NaCl plus H2O solution, and then there is a big chunk of barium sulfate that you will be having. So you just need to filter this on a filter paper, and so use a conical flask like this and take inside a beaker. So pour this solution on. So the barium sulfate will remain here, and all NaCl filter NaCl solution will come. So just take this barium sulfate, dry it out, and you will have a dried barium sulfate. Then for NaCl, just heat it. It will remove some excess water. It will become more saturated NaCl solution, and then make it to cool down at room temperature. Put a string of you can say with the strings of a small crystal of NaCl, and suspend it inside the beaker, and you will see that there will be a big chunk of NaCl crystals gathering around that string, and then that's how you can easily make the crystal. So this is one way of putting it. So let's write it in words. Put the mixture of solids in a beaker and add water to it. Slightly heat and stir the beaker. So what will happen? So when we stir the beaker in heat, the sodium chloride in the mixture will dissolve and barium sulfate will remain in the beaker. Okay, then and you can say NaCl will dissolve whereas space will remain insoluble. Okay, then place a filter paper inside a funnel and pour the mixture through the funnel into another beaker. The insoluble barium sulfate will be collected inside the filter paper wash the filtrate with H2O or distilled water and dry it to collect the barium sulfate. Then remember, we have to make pure crystals of sodium chloride. So basically, the concept or the way to crystallize any salt from its saturated solution is something we are interested in. So first of all, we have to make a saturated solution of sodium chloride by heating it. Then slowly heat the NaCl solution in the beaker till a saturated solution remains. Then add a string of NaCl or sodium chloride. No, add a, or you can say a seed crystal or a string of sodium. Add a string to the beaker and allow it to cool at room temperature, or you can call it as slow cooling. So what we'll get? Pure crystals of NaCl will be collected across the, or will develop across the string, or can be collected across the string. Okay, so this is how you can easily make or collect pure crystals of sodium chloride. Okay, so moving ahead, question number 3, it says a student measures temperature change during a reaction between hydrochloric acid HCl and aqueous sodium hydroxide or NaOH. NaOH, and then equation is written NaOH plus HCl, NaCl plus H2O. So acid plus base, salt and water. Number part A, it says the student uses a measuring cylinder to add 25 centimeter cube of 1.5 mole per decimeter cube sodium hydroxide to a glass beaker, records the temperature of sodium hydroxide, add 4 centimeter cube of HCl to the beaker and record the highest temperature reached. Adds further 4 centimeter cube portions of HCl and records the highest temperature reached each time. The student results are shown. So name the type of reaction that takes place between HCl and NaOH. So this is actually a neutralization reaction, or we can, in terms of heat, we can also say that it is an exothermic reaction because it is releasing heat to the ground. So it is a neutralization reaction. And we can also call it as exothermic reaction. Okay. So moving ahead, it says name a piece of apparatus that can improve the accuracy of volume of sodium hydroxide added to the beaker. So we can use a pipette or a burette. Burette. Then it says name a piece of apparatus used to add 4 centimeter cube of HCl. It is burette. Then it says explain why a glass beaker is not the most suitable piece of apparatus for this experiment. So remember, there is if the student is measuring the heat, so the glass can absorb some of the heat, and that is the result would be heat loss to the surroundings. So explanation: the glass beaker absorbs heat and results in heat loss to the surroundings. An improvement can be insulate the beaker, in this way, we may prevent the heat loss to the surroundings and will have much better readings. Moving ahead, it says plot the values of temperature against total volume of HCl on the grid. So remember, on the y-axis, they have given us temperature. On the x-axis, they have basically given us volume or that is in centimeter cube of HCl. So let's start to draw these points. So at 0, we have 24.5. At 0, we have something like this. At 4, we have 25. So at 4, we have 25. Then at 8, we have 28.5, 28.5. Then at 12, we have 30.5, 30.5. Oh, so at 12, we have 30.5. At 16, we have 32.5. 16, we have 32.5. At again 20, we have 32.5. Again, and at 24, we have 31.5. At 24, we have 31. 24, we have 31.5. At 28, we have 30.5. 30.5. And at 32, we have 20. We have 29.5. So this is what we have. And the first part is, it says, plot the temperature. So we have plotted the values. Then it says circle the anomalous point on the grid. So anomalous point, so we have basically circled it all over here. Let me circle it with a blue color. So this is the anomalous point. So for part 6, this is the answer. Then say draw best fit straight line to the points from 0 to 16. So best fit straight line from 0 to 16. I'm drawing it with the say blue color. So if so it's always good to draw a best fit straight line since I don't have much good drawing facility on my writing board, but I'm trying my best to give you a straight line. So I mean, you'll have a ruler that will give you a good straight line. So this is a good straight line. Draw a good straight line from 20 to 23. So if I'm going to draw a line, it would be something like this. So extrapolate both lines till they exceed. So once you basically draw these lines in third point, you extrapolate and use the intersection point to determine minimum volume of HCl needed to react with all the sodium hydroxide. So this will be, or where this X will interact, that will be your value. So if you're going to use a graph, so its value will be something over here. I would say it would be something value would come in this domain. So I apologize for the bad drawing. So if you're going to measure this value is approximately 17.5 or so you can say 5, 6, anything you can say. So approximately 17.5, 17.6 would be good. So we'll take 17.6. So extrapolate, extrapolate. So this value will be 17.6 centimeter cube HCl. So we have circled the anomalous point, drawn the straight line, both the straight lines, extrapolated them, and where they have intersected that point, and we've used that value to be as the minimum volume of HCl needed to react with all the sodium hydroxide. So then part 10, use the information to determine the temperature change due to the reaction. Remember the temperature change in the reaction, or delta T. The maximum temperature that has reached is from the graph, which we can see is something over here. Or from the table, if we are going to go back from the table, the maximum temperature we can see is 32.5 degrees centigrade, and then the minimum temperature, it started from 24. So again, the maximum temperature here is 32.5, minimum is here. But remember, what we have done over here is we have extrapolated it. So once we have extrapolated it, what we can see is this has reached something over here. So it will be around something 32.2 degrees centigrade, to be very exact, if we are going to. So this is the maximum temperature that has been reached. So if we are going to find out delta T, so that will be T max minus T minimum. So T max, so it would be 33.2 degrees C minus temperature minimum, that is 24.5 degrees centigrade, and delta T would be 8.5, not 6. So 8.5 degree centigrade, or in so this will be 8.5 degree, or I mean your marking scheme, it says 8.7. So that is also fine, depending on how you draw it and on your paper, that would be good. Then it says part 11, the heat change during the reaction is calculated using the expression shown. Heat change, mass of sodium chloride, specific heat capacity, and temperature change. So remember, M C theta or delta T, heat change, Q equals to mCt. 1 centimeter cube of this solution has a mass of 1 gram. Determine the value used for the mass of the solution to calculate the heat change. So, remember, mass of HCl, so volume of HCl multiplied by 10 grams. The volume is 17.6 multiplied by 1. So we have 17.6 grams. And similarly, mass of NaOH, sodium hydroxide, is 25 centimeter cube multiplied by 1 equals to 25 grams of sodium hydroxide is used. So then the mass of solution in the calculation of heat change. So remember the overall mass. So the solution contains NaOH, that is 25 centimeter cube, plus HCl, that is 17.6 centimeter cube. So if we are going to weight this solution or measure the mass, that would be the sum of these two solutions that are inside the overall solution. And this is the complete mass that is, or heat that is being absorbed or changed. So if we add them, so both add them, and it comes out to be 42.5, 42.6 grams. 17.5. So mass of this is 42.6 grams. Then moving ahead, it says part B, it says actual heat change of this reaction is much greater than the value calculated using the expression in part 11. Suggest a reason for this difference. Also, the sum of the heat has been absorbed or lost by the to the surrounding by the beaker. So some heat has been lost to the surrounding and absorbed by the beaker. Okay, so this is how we can easily write and say this. Next, moving on, question number 4. In question number 4, it says the apparatus is shown is used for electrolysis of dilute sulfuric acid to produce hydrogen gas and oxygen gas. The electrodes are made up of platinum. Give the name of each electrode. So this is your positive electrode, this is your negative electrode. So positive electrode is an anode, negative electrode is a cathode. That's the technical names. So the electrodes are made of platinum, name of each. So positive electrode is anode, negative electrode is cathode. Then part B, it says equation for the reaction at positive electrode is shown. Give the equation for the reaction at negative electrode. So for positive electrode, the equation is shown at positive electrons. Remember, there is a loss of electrons, and it means that there is a reduction that is taking place. On the negative electron, there will be gain of electrons. That means that it will be oxygen. It will be the oxidation that is taking place. So on the positive electrodes, we have H positive that will be gaining electrons, and hydrogen gas will be released. So now balance it. So 2 electrons, 2 electrons. So then it is balanced. So that, remember, this is oxidation that is taking place, and or gain of electrons that is happening. Let me change to red color. So now moving ahead, it says describe the test used to identify the gases that are produced. So remember, on the positive electrode there is water and oxygen gas, and on the negative electrode there is hydrogen gas. So on the test for oxygen, the burning splint test. So test is collect gas in a test tube, or you can say collect gas in an inverted test tube. That is the way. Collect the gas in an inverted test tube. Take a glowing splint inside it. Okay, observation. The glowing splint rekindles the glowing splint rekindles inside the test tube. So remember, oxygen supports combustion. So that is the way we can test for this gas. So hydrogen, again, take a glowing splint inside a test tube containing gas. We'll hear popping sound will sound is heard. So this is a test for the hydrogen gas. The hydrogen gas produces popping sound. Moving ahead, question number 5, it says a student uses the apparatus to investigate the rate of reaction between excess copper carbonate and dilute sulfuric acid. So remember, copper carbonate is in excess of excess and dilute sulfuric acid. So identify the piece of apparatus labeled X. So labeled X is gas syringe, gas syringe. Okay. Then it says a student starts reaction by tipping a sample tube so that copper 2 carbonate and acid comes in contact. Okay. Explain why this method is used instead of adding copper carbonate to the acid and replacing the bung. So, I mean, if we are going to add uh, uh, copper carbonate, it will immediately react with the acid inside, producing gas, and will not be able to completely collect the gas. So in this manner, there will be no gas leakage, and we'll be easily able to collect all the gas that is produced. So this allows complete collection of gas produced without any loss to the surrounding. Okay. Then it says part C, it says the student takes reading of the apparatus after every 10 seconds until the reaction has stopped. The student plots the graph of these results. Okay. And then it says give labels for each axis on the graph. So this is, for example, your x-axis, and this is, so say, your y-axis. So this is actually your vertical axis, and this is your horizontal axis. Generally, it is good to have time on horizontal axis or measured in seconds after every 10 seconds. So you can say 10, 20, 30, 40, 50, 60, 70, yeah, or any. And then on y-axis, there will be volume of. So on the y-axis, you can calculate the, or write down the volume of gas measured in centimeter cube. Okay. So give the labels for each axis. So we have, okay. So on the horizontal axis, on the x-axis, which is time measured in seconds. On the vertical axis, volume of gas centimeter cube. Okay. Then it says list 3 things the student sees happening in the class during the reaction. So first thing, what will happen inside the glass? So there is this solid carbon dioxide, solid copper sulfate carbonate. So this is a in axis. So what will happen? The mass of solid carbon dioxide starts to decrease. Then it is collecting carbon dioxide. So then there will be effervescence of carbon dioxide, and it's a copper carbonate that is reacting, and copper sulfate is bluish in color. The color changes from colorless to blue. So these are the 3 observations. So first of all, mass of copper carbonate decreases. Effervescence oh, effervescence or bubbles of CO2 gas are reduced. Solution changes from colorless to blue because of copper sulfate, or because of copper sulfate. These are the two observations. Then it says use the graph to explain what happens to the rate of reaction. So if we see the graph, we can see that initially as the reaction starts, say it starts from here, so this is the zero of the graph, the rate of reaction is the highest, and as the reaction proceeds, the rate of reaction, say if we have 3 points A, let's say B, and let's say 3. So the rate of reaction, if we measure the slope here, it is great, then it is slope here and then here. So we have the maximum slope at A, then B, and then C. So maximum at A, minimum at C. So as from the slope, we can say that the rate of reaction decreases as the reaction proceeds. Simply, we can say that the rate of reaction decreases as the reaction proceeds. The slope is greater initial and decreases to 0 as the reaction completes. Okay, so you can simply say that rate of reaction decreases as the reaction proceeds, and the rate of reaction becomes 0 as the dilute sulfuric acid is totally, as the reaction completes, or you can say dilute H2SO4 is consumed. Okay, so this is how we just simply write this. So again, so this is the last question for this exam, and I hope you have enjoyed this video. And in case you have any questions, please feel free to write in the comment section. And I wish you best of luck for your exams and happy preparation. See you next time. Bye-bye.